Hello everyone, my name is Sonia Ruiz Pérez, the Product Manager of the EFFECTS and RISKCURVES software tools, and I would like to welcome you to the third part of our video series, CO2 Hazard Modeling with Effects and Risk Curves for CCUS pipeline transportation. Today, we'll be discussing the challenges of modeling CO2 releases from pipeline failures. But before that, let's look at what happens during a pipeline failure to understand the complexities involved. When a pipeline fails, the chain of events differs depending on whether the pipeline is above ground or buried. For above-ground pipelines, a puncture or a rupture causes the release of pressurized CO2 as a high-velocity jet. This jet entrains air and it typically exits vertically, but environmental factors like wind or nearby structures can alter its trajectory. For buried pipelines, a rupture causes the pressurized CO2 to displace soil, forming a crater. This causes the CO2 jet to emerge vertically from the crater. The crater's size and the soil's properties affect the release dynamics, including jet velocity, dispersion, and potential phase changes. In both scenarios, the rapid expansion of CO2 results in significant cooling. It often transitions into a mix of gas and solid dry ice, creating a dense cold vapor cloud. This cloud stays close to the ground, spreading along the terrain. It's influenced by wind and terrain conditions and displaces oxygen, creating an asphyxiation risk. Understanding these chains of events is essential for accurately assessing and developing effective safety measures for the associated risks. As mentioned in the previous video, hazard modeling plays a vital role in simulating these scenarios and predicting how CO2 behaves during an accidental release. However, accurately modeling CO2 releases comes with its own set of challenges. Now, let's look into these modeling challenges. The first challenge lies in the multi-phase nature of CO2 releases. So during a high-pressure release, CO2 undergoes rapid depressurization within the pipeline, causing it to flush into a mix of gas, liquid, and solid phases. These phase transitions occur much faster than those of other liquefied gases, adding complexity to the modeling process. Advanced thermodynamic models are required to accurately simulate these behaviors. For buried pipelines, the release dynamics are significantly influenced by the size and the shape of the crater and the properties of the displaced soil. Overlooking these factors can lead to inaccuracies in modeling dispersion, velocity, and phase behavior. On the other hand, standard evaporation models often fail to capture the sublimation process of solid CO2, or even the spreading of CO2 behavior from a crater, adding complexity to the scenario. The next challenge is determining the exit conditions of CO2, which depend on pipeline pressure and temperature at the point of failure. At high pressures, when CO2 behaves as a pressurized liquefied gas, rapid depressurization can create a two-phase jet of vapor and solid CO2. Accurately predicting these exit conditions is critical because they determine the downstream behavior of the release, including jet velocity and spread. Additionally, carbon dioxide's dense gas nature requires specialized dispersion models. That is because dense clouds tend to flow along the terrain and accumulate in low-lying areas, potentially creating oxygen-deficient zones. The presence of solid CO2 particles adds complexity as sublimation affects the thermodynamics of the dispersing cloud. Moreover, environmental factors such as wind, terrain, and atmospheric conditions heavily influence CO2 dispersion patterns. In flat terrains, dense CO2 clouds may spread uniformly, while in hilly or confined areas the gas may pool. On the other hand, variations in temperature or humidity can alter sublimation rates, impacting dispersion. Now that we have identified these challenges, it's clear that accurate modeling of CO2 releases requires careful consideration of all of these factors. Ignoring elements like phase transitions, crater effects, or environmental conditions can result in inaccurate predictions, compromising safety decision-making. However, performing this level of detailed modeling manually is both time-consuming and complex. That's where tools like EFFECTS and RISKCURVES, they play a crucial role. These software tools are designed to address the unique challenges of CO2 hazard modeling, providing reliable predictions of CO2 behavior under various conditions, as well as advanced simulations that account for phase transitions, crater formation, and environmental conditions. This ensures you have the insights needed to make informed, safety-critical decisions for CCUS projects. In the next video, I will demonstrate how EFFECTS tackles these modeling challenges. I will also share snapshots of the software in action and examples of calculation results so that you can see firsthand how these tools can enhance your safety projects. Thank you very much for watching, and I look forward to seeing you in the next video.